In this segment, we're going to begin to look at the key type of reaction that alkenes undergo. And that key type of reaction that alkenes undergo is referred to as an addition reaction. So what we will do in this segment is we'll introduce the concept of what we're talking about when we say addition reaction, and then follow with some key terms related to describing addition reactions and describing reactions in general. And then from there, we'll go onward to some additional segments, additional videos, where we will look at specific types of addition reactions that alkenes can undergo. So right now, what we're trying to do is lay the foundation for the next few segments, where we'll be looking at specific reactions of alkenes with a focus on different addition reactions. So let's go ahead and get started with no further ado, looking at the concept of addition reactions. When we're talking about addition reactions, much as the name implies, we're referring to adding groups or atoms across the carbon-carbon double bond. So our generic addition reaction for alkenes is that in general, we're going to start with an alkene molecule. So we have to have a carbon-carbon double bond in there. I'm going to go ahead and plug in R groups attached here. So these could be carbon chains, hydrogens, whatever. The main thing that you need to be looking for is that there is an alkene group present in the molecule. And what we'll be doing then is taking our reagents, which we'll call XY. So XY has to be at least 2 atoms. They could be 2 identical atoms, such as Cl2 or Br2, or it could be 2 different atoms, such as HCl, HBr, etc. And we're going to be adding those 2 atoms or 2 groups across the carbon-carbon double bond. So one of the 2 atoms or groups there, X and Y, is going to form a new bond to the carbon of the alkene group on the left. The other is going to form a new bond to the carbon on the right. So as a result of an addition reaction, what's going to happen is that we'll no longer have a carbon-carbon double bond there, but instead it'll be a carbon-carbon single bond connecting the 2 carbons together. So we go like this. And then we will have added across that carbon-carbon double bond our 2 new groups, X and Y, like so. So we would describe this product as being the addition product, because we've added X and Y across the carbon-carbon double bond, and to allow us to stay within the octet rule, we have had to have gotten rid of the alkene group along the way as a result of this so-called addition reaction. So we describe this as the addition product. So we're going to spend the rest of this chapter on addition reactions looking at the specific reagents that we will use to carry out these addition reactions. In other words, what can we use as X and Y to allow us to do addition reactions? How can we take these alkenes that we start with as our starting materials and convert them in to the so-called addition reaction product? So what I want you to keep in mind here is that whenever you see an alkene group in your starting material, be on the lookout for the general type of reaction that alkene groups will undergo as being an addition reaction. So you'll look at the alkene group present there in the reactant, and you'll ask yourself, are there any 2 atoms or 2 groups that can add across that carbon-carbon double bond? And we'll go through the specifics of what types of groups and what types of atoms are suitable here to act as X and Y, to act as the reagents that are adding across the carbon-carbon double bond. Before we get onward with that, looking at the specifics of addition reactions and going through a series of specific examples of reagents that we can use and the mechanisms for those reactions, I want to first define a few terms that you will see over and over again throughout this chapter and also throughout other chapters. And a couple of these terms are ones that we have mentioned previously. So the general terminology that we will use in association with addition reactions and other types of reactions is we can throw out the term regioselective. So when we're talking about terminology, one term that we can use oftentimes to describe reactions is we can describe them as being regioselective. So the term regioselective is referring to a reaction that has a preference, or it selects a specific, in this case, constitutional isomer over other possible constitutional isomers that could hypothetically form. So regio refers to regioisomer, which is a type of constitutional isomer. So we're talking here about reactions that are selective for what constitutional isomer is preferred. So we're going to define this as a reaction with a preference for yielding certain constitutional isomer product over others that are hypothetically possible. So reaction with a preference for yielding certain constitutional isomer products over others that are theoretically possible. So over others that are theoretically possible. The other wording that we can ascribe to the term regioselective is we can also describe it as a reaction that, in theory, could yield multiple constitutional isomer products, but in actuality has a preference for only a subset of these. So in other words, theoretically the reaction could yield perhaps two different constitutional isomers, but in actuality we see that one of those is a major product and the other one is a minor product or not observed at all. That would indicate that the reaction is indeed regioselective. So let's take a look at just some general examples of describing the term regioselective. Let's take a look at this problem where we have an alkene starting material reacting with X and Y, which are our adding reagents. And we've defined that X and Y represent two different groups. So for example, an H and a Br or something like that. So we have out of this reaction two different possible constitutional isomer products depending on where we put X and Y. So if we put X here and Y here, that's going to give us a different product than if we were to instead put Y here and X over here instead. We could draw two different products that correspond to that. And that's exactly what I'm going to do here. So I'm going to color code this. I'm going to put in blue the product that would correspond to the scenario that we showed in blue there with our dotted lines to start mapping out where atoms are bonding. So this would be one of our possible constitutional isomer products corresponding to adding X and Y across the carbon-carbon double bond, where group Y adds at carbon number 2, group X adds at carbon number 3 of the chain. The other possible product of this reaction is that instead we could switch where X and Y are adding so that we put X adding here at carbon number 2 and Y adding at carbon number 3. And what you will see is that the relationship between these two molecules is that of constitutional isomers. Because keeping in mind that X and Y we've defined as two different atoms, what we see is that in one of those cases the branch to X is at carbon number 2, in the other case the branch to Y is at carbon number 2. So that means that these are going to be related to one of those constitutional isomers. So if each of these two compounds were formed in equal quantities, we would say that the reaction is not regioselective. So I'm going to go ahead and write that down, that the reaction is not regioselective if those two constitutional isomers, the two theoretical products, are yielded in equal quantities. So the reaction is not regioselective if the two hypothetical constitutional isomers are in actuality observed in equal amounts. So if we see that there's a 50-50 split between these two constitutional isomers, that means the reaction is not regioselective. It means that it's just randomly choosing to put X or Y at carbon number 2 and X or Y at carbon number 3. On the other hand, if one of these two molecules is present in abundance relative to the other one, in other words, if say we make 90% of our yield is the product in red, 10% is the product in blue, that would indicate that the reaction is regioselective. So I'm going to go ahead and write that out, that the reaction is regioselective if the two hypothetical constitutional isomers are not observed in equal amounts in the actual product mixture. So the reaction is regioselective if the hypothetical constitutional isomers are not actually observed in equal amounts. So this means that the reaction selected to make one product over the other. And this is a term, regioselective, that comes up with regard to describing a lot of different types of molecules. So it's really important that you get the terminology down here of what we're referring to when we say that a reaction is regioselective. It's referring to a situation where the hypothetical product mixture that we could form, meaning if we're randomly putting X and Y across the carbon-carbon double bond, does not match up with what we actually observe at the end. At the end, we observe that we have a preference for one product over the other, meaning that there is regioselectivity taking place. You can think of regioselectivity as meaning constitutional isomer selection. We're preferring one constitutional isomer over another possibility. So we're not making all of the different possibilities of adding X and Y across the carbon-carbon double bond. Now, when we're trying to assess whether or not a reaction is regioselective, one thing to keep in mind is that if the two groups being added are identical, for instance, adding a chlorine atom at carbon number 2 and a chlorine atom at carbon number 3, then the reaction cannot be regioselective. So let's look at an example of what I mean by that. So we're going to take our alkene molecule here and we'll react it with what is a common addition reagent, Cl2. In the addition reaction with Cl2, we're going to add chlorine to carbon number 2 and carbon number 3 of the chain there across the carbon-carbon double bond in a typical addition reaction. So we'll go ahead and draw the product that would result from that. So I'll go ahead and draw in my carbon skeleton. And then our chlorine atoms, I'm going to show those as two different colors to represent the two different chlorine atoms. So I'm going to show the two chlorine atoms as a chlorine in green and a chlorine in red, keeping in mind that these are indeed identical atoms. So I could add the chlorine in green to carbon number 2 of the chain, the chlorine in red to carbon number 3 of the chain, like so. And with this particular example where we have two atoms that are identical in the addition reagent, the other product that we could make, or the other hypothetical constitutional isomer, is actually not going to be a constitutional isomer of this other structure at all. Instead, it's going to be identical. So say we put the red chlorine at carbon number 2, green chlorine at carbon number 3. These two structures that we've just drawn actually turn out to be identical. And so therefore, this particular reaction cannot be described as regioselective because there's only one possible constitutional isomer product that can result from that, and that is indeed what we make. So in order for a reaction to be regioselective to start with, it has to have two different possible constitutional isomer products that can hypothetically be formed, and it has to favor one of those two. In this case, since the two products we showed there on the right are exactly the same, they would both be described as 2,3-dichloro molecules, then we can't describe this reaction as being regioselective. The reaction is definitely not regioselective, and the general rule that I'm going to give you for this is as follows. The general way that we can state this is we can say that for a reaction to be regioselective, both reactants have to be asymmetrical. If either of the two reactants are totally symmetrical, such as here we're adding a chlorine to each of the two carbons of the carbon-carbon double bond symmetrically, then the reaction cannot be regioselective. For it to be regioselective, you have to have an asymmetry in both of the two reactants. So up top, we illustrated how the reaction can't be regioselective if what you're adding across the carbon-carbon double bond is two identical atoms. Right now, what we'll show is that if the alkene molecule is symmetrical, we will not be able to have a reaction that is regioselective either. Okay, so we take a look at this problem at the bottom of the page, and you'll notice here that our alkene molecule is symmetrical. Relative to our carbon-carbon double bond, we have a methyl group attached to both sides. So what's going to happen is once we do the addition reaction, we add X and Y across the carbon-carbon double bond. I'll go ahead and show X and Y in red here for emphasis, adding Y and X. And then say we go ahead and do it the other way, flipping which location gets X and which location gets Y. So I'm going to put Y over here and X over here to give us are two hypothetical products, but what is the case here is you'll notice that the two hypothetical products, if we came up with an IUPAC name for those, we would come up with exactly the same name. Same name means same structure, same constitutional isomer in other words, and so this reaction is definitely not regioselective either, just like the one up top. And this illustrates again that principle that if either of the two reactants that are going into this reaction to yield the final product are symmetrical, the reaction cannot be regioselective, because here, based on the fact that our alkene is symmetrical, when we add X and Y across the carbon-carbon double bond, we're going to see that no matter which orientation we do it, in terms of X and Y bonding to the left versus the right carbon, we're going to end up with the same constitutional isomer one way or the other. So therefore, the reaction is not regioselective. Now we use a second term to describe the outcome of chemical reactions, and that second term is the term stereoselective. The term stereoselective also came up with regard to nucleophilic substitution reactions, so we're not going to go into it in as much depth here, but it is certainly something that you want to keep in mind with regard to looking at the outcomes of chemical reactions. A stereoselective reaction is a reaction that in theory could yield multiple stereoisomer products, but in actuality prefers just one or a subset of those hypothetical possibilities. So much like regioselective refers to reactions that are selecting certain constitutional isomers, stereoselective refers to reactions that are selecting certain stereoisomers. So let's take a look at an example of that as applied toward addition reactions. So let's take a look at this example problem where you're given an alkene starting material. You're told that the alkene reacts with X and Y, where X and Y represent two different atoms, and then here's the product set that we get. So we're using the term stereoselective and going back also to that question of whether the reaction is regioselective. So I'm going to step back a moment and ask, with a little checkbox here, whether the reaction is regioselective. And now would be a good time to hit the pause button and make sure that you do understand the term regioselective by looking at the products that are formed from this reaction, asking yourself whether the reaction is regioselective or not. So please think about that before continuing onward here. Is the reaction regioselective? The reaction is regioselective here in this case because, so I'm going to put a Y there for yes, when we look at where the groups X and Y, which are two different atoms, bond, we see that Y always bonds at carbon number 2 of the chain in all 4 of the observed products, whereas X always bonds at carbon number 3 of the chain. So that fact that we never see X at carbon number 2 and Y at carbon number 3 indicates that the reaction is selecting that X goes at carbon 3 and Y goes at carbon 2. We see only one constitutional isomer product here. We don't see multiple constitutional isomers. What we do see are a range of different stereoisomers. So we need to ask whether this reaction is stereoselective or not. And so to ask whether the reaction is stereoselective or not, what we will do is ask how many different stereoisomer products are possible out of this reaction in theory, and how many do we form in actuality. So the trick for asking about stereoselectivity is ask yourself number of stereoisomers that could be formed in theory, and you can solve that by using the 2n rule, where n equals the number of newly formed chiral centers, or the number of chiral centers that are impacted by this reaction. So if there were chiral centers elsewhere in this molecule, somewhere far, far away, you wouldn't worry about those in your 2 to the n rule here. We're looking at how many different stereoisomers can arise from this particular reaction, so we're only focusing on chiral centers that would be formed as a result of reacting here and here at carbon 2 and carbon 3 of the chain, the 2 alkene carbons. So looking at this reaction, each of those 2 carbons that I've put the blue dots on in the final product will represent chiral centers, and therefore the number of stereoisomers in theory for this particular reaction doing 2 to the n would be 2 to the 2, or 4 stereoisomer products in total is the theoretical number that is possible. And as we look at those 4 structures there, we notice that those 4 structures we've drawn are related to one another stereoisomers of various sorts by using and comparing those wedges and dashes. So for this particular reaction, In theory, we can yield 4 stereoisomers. In actuality, we actually make 4 stereoisomers, so therefore we would say the reaction is not stereoselective. So I'm going to put an N for no. The reaction is not stereoselective. So here, to go back to that rule or guideline, the number of stereoisomers in theory being equal to 2 to the n. If the actual number of stereoisomers is less than the theoretical number, that indicates the reaction is stereoselective. So if actual number of stereoisomer products is less than the theoretical, based on the 2 to the n rule, the reaction is stereoselective. On the other hand, if the actual number of stereoisomer products is equal to the theoretical number that could form, then the reaction is not stereoselective. So that's why we say the reaction that we've shown here is not stereoselective, is because the number of theoretical stereoisomers equals the number that is actually observed. Now, if instead what we did was said that our products of this reaction looked like so, let's take a look at version 2.0 of this example problem, asking again the question of whether the reaction is stereoselective or not. So we had our alkene molecule reacting with X and Y. We defined X and Y as 2 different atoms. We established that this reaction already was regioselective because we always put Y at carbon number 2 and X at carbon number 3, never the reverse, meaning X at 2 and Y at 3. And now we're going to ask, is the reaction stereoselective? Again, I always encourage you to hit the pause button right now and ask yourself that question of whether this is stereoselective or not. The answer is that yes, this is stereoselective because in theory, we have 2 chiral centers in our product, here and here. And so therefore, the theoretical number of stereoisomer products that we could yield out of this reaction is equal to 4, using that 2 to the 2 rule. But in actuality, we see that we're only observing 2 of those 4 possible stereoisomer products. Therefore, the reaction is described as being stereoselective because we're not making all 4 products. Instead, we're making just 2 here. And these 2 that we're making happen to be enantiomers of one another, and that is a very common thing that we will see for stereoselective reactions, is that we'll end up with 4 different stereoisomer products possible out of the reaction, but in actuality only 2 that are related to one another as enantiomers are formed out of the reaction. So stereoselective is another term that we'll be on the lookout for as we look at addition reactions. We're generally going to be asking ourselves for each reaction, is the reaction stereoselective? Is the reaction regioselective? It can be one, it can be both, it can be neither. So you have to look at each one on a case-by-case basis. So in this case, this particular reaction we said yes, was stereoselective. What we'll do in the next several segments is go into specific examples of what scenarios we can run into when we look at addition reactions. In other words, what atoms or groups can be X and Y, what types of other rules do we need to think about when we're deciding where to place X and Y across the carbon-carbon double bond? In other words, how can we predict the regioselectivity of a reaction? How can we predict the stereoselectivity? And what types of cool things can we do with these types of reactions? So stay tuned for the next several segments on that.